To see you in
our seminar, Analysis of Applied Mathematics. I would like to invite Professor Dr. Yury Shestopalov, University of Gävle, for presentation. He's the best special in theory of operators and applications of mathematical and electrodynamics, methods of solution to inverse problems, and problems with this uncertain data, wave propagation, nonlinear media, and nonlinear operator equation, integral equation, partial differential equation, numerical method optimization, applied computer codes, servers, and program package. As you know, you're a best mathematician and best friend. So you are welcome.
Thank you, Alabarian. It's my great pleasure to be invited by Professor Asher Aliyev to Banchishehir University and to Istanbul. My affiliation here is missing. I am with the University of Gävle in Sweden, and this is my partial affiliation in Russia. This is the biggest technical university in Russia now. It's about 75,000 students. It's a huge university and situated very close to the People's Friendship University on the same street, by the way. So this is my second affiliation. I will speak about, actually, in the beginning, very simple things, because an idea is that this lecture was intended also to students and PhD students. So the things in the beginning will be very simple. So I will talk about one-dimensional Sturm-Liouville problems for Helmholtz equations, then how the results can be extended to more or less real diffraction problems in open domains, external boundary value problems, then how the results may be applied to the analysis of resonances and invisibility or anti-resonances. And the main result, mathematically central, is existence of resonance scattering frequencies for dielectric cylinder of arbitrary cross-section. This is a very recent result. So the achievements, and I want to make actually a short review to give colleagues also in this university to see the problems of interest which may be attacked by colleagues. So this group of problems is related to applications of non-self-adjoint operator spectral theory in electromagnetics and acoustics. And I give references only to my work. This is not modest, but just to give a short review. So some references are here, and we consider external boundary value problems and eigenvalue problems for Maxwell and Helmholtz equations in open domains connected with scattering by dielectric cylindrical scatterers, especially of possessing circular symmetry. And our interest is to mainly show the existence and study the distribution on the complex plane of resonance parameter values and resonance or scattering frequencies of different types of scatterers. So here is a short list of publications related to the topic, and I can provide access to this list to any colleague, and I leave the file at the seminar of the presentation. Most of the papers are in open access, so it is paid open access. So my name is enough to find if someone is interested in the papers. So historically, the studies were connected with the works of Goldberg, mainly with Goldberg and his school. And this was related to spectral or eigenvalue problems for non-self-adjoint operators, where the operator is nonlinear with respect to the spectral parameter. So this is the background. And the topic has been discussed many times also at Moscow State University with professors Ilyin, Alimov, Sadovnichi, and many others. Some 50 years ago, so it's a long history behind it. And what is one of the ideas that I want to present today? So if we consider an external boundary value problem for Helmholtz equation, to be precise, then outside a circle of sufficiently large radius, the solution may be decomposed into these Fourier series, where the coefficients Tn, Hn1 are solutions to Bessel equations, one of the solutions to the Bessel equations, which satisfy the so-called radiation conditions at real parameter k0. So if we consider a scatterer, then outside a circle containing the scatterer, the following representation 1 holds, and coefficients Tn depend on the problem parameters. And we want to study the properties of solution considering these expansion coefficients as functions of parameters. It seems to be not a very good idea from the beginning. However, it has proved to be efficient recently, and many results have been obtained just in this direction. So obviously, resonance scattering or anti-cloaking. Cloaking means, in a sense, invisibility, is connected with singularities of the expansion coefficients when they are considered with respect to a certain problem parameter, complex parameter. And zeros of these coefficients provide in many cases cloaking, that is, suppression of the solution norm in a certain spatial domain. So both resonances and invisibility or cloaking can be investigated in terms of the analysis of these coefficients. And this idea has proved to work remarkably. So if the first with these indices coefficients vanish simultaneously at a certain parameter set, then we have the so-called suppression of the principal harmonics, and clear cloaking or effect of invisibility is observed. So if we manage to find the parameter set at which the principal coefficients vanish simultaneously, then we have a deep invisibility, so to say, at this parameter set. And when the coefficients, as I have already said, are singular, then we have resonance frequencies, and we have singularities of the solution to the initial BV. Now a very simple part. I'm sorry, very simple things I will tell now. So if we consider two operators, one-dimensional Helmholtz, when k is 0, we have Laplace operator in one dimension, or Bessel differential operator of 0 order, then the solutions to the former are trigonometric functions, And the solutions to the latter are, I'm sorry, maybe, Bessel functions, it is clear. Bessel, Neumann, or Hankel functions of this form. And we know that both these function families have zeros, infinitely many simple zeros are presented here. This is a graph of the Bessel function, zeros, and this is Neumann function. And if we, by the way, the distance between zeros of Bessel functions and sine is pi. So the distance is the same, by the way. It's about pi. The same zero distributions of these functions. So if we consider four Sturm-Liouville problems for Laplace equation on the unit interval, first kind, Helmholtz unit interval, first kind, Laplace and Helmholtz, third kind with parameter alpha, then eigenvalues are as follows. And if we consider Helmholtz operator as a shifted Laplacian, the eigenvalues will be shifted by parameter k. And for the third kind Sturm-Liouville problems, to obtain eigenvalues, we have to solve a certain transcendental equation to look for zeros of this function. This is, of course, trivial. This function, geometrically clear, has infinitely many simple positive zeros located close to zeros of the cosine function. We can very easily check fundamental properties. So depending on parameter alpha, they form an increasing sequence Sn alpha located in between zeros of the sine and cosine functions. And they have the same asymptotics as zeros of sine function. However, if alpha is complex, which is the case in external problems, the existence of zeros is an open question. Immediately we have a problem. If alpha is complex, the question is if complex zeros exist. And if they exist, where they are located. I will not answer to this problem. I will just state that by multiplying by cosine, we reduce the problem of finding zeros to finding zeros of the so-called weighted generalized trigonometric polynomial of order 1. So the weight is here. For real alpha, no problem for finding, but for complex alpha, it's a kind of a problem. So how to find zeros in this very simple case? Reasonable to apply parameter continuation method to consider zeros as implicit functions and to reduce finding zeros to the solution of this initial value Cauchy problem. It has a unique continuous solution in the vicinity of every point. It is easy to check the conditions. So this is a practical way to find zeros for more or less arbitrary alpha using parameter continuation. This method can be applied for complex alpha, and this is good, but not as easy as in the case of real alpha. But this is a practical way to find zero. Now, why zeros are important for the resonances? If we consider the problem with the right-hand side on the unit interval, and if we assume that f support belongs to the domain of the operator, that is, f can be decomposed into the sine Fourier series with coefficients fn, then the solution is immediately obtained by the spectral method in this form, and or in terms of Green's function. And clearly, all coefficients have the form of ratio of known Fn and lambda n of k. That, therefore, as we all know, the coefficients have singularities when k coincides with eigenvalues of Lk or all of Laplacian, and the solution has singularities at the same point in k. For example, if we separate the first term, we see that it is singular when k is equal to pi, that is pi is the first resonance. As this is well known, of course, but what is important for us, that having this series obtained by the spectral method and considering singularities of the coefficients, we obtain resonances or eigenvalues. So this is approach from the other side. And this form of the coefficients will be preserved in much wider family of problems. So, as I already said, if alpha in the third kind BVP is complex, then we have to look for complex zeros of this function, which is actually an open problem. But we are interested in non-local BVP on a semi-axis. So on the interval null A, we have Helmholtz with K1, and on a semi-infinite interval, we have Helmholtz with K0, and epsilon is their ratio, and we may assume that it is a real number greater than 1, which is physically justified, and the conditions at the point of discontinuity is as follows. And this is asymptotics sign, but we can choose any other asymptotics, but we choose sign. Then looking for the solution in this form, we immediately obtain that eigenvalues will be zeros of this weighted trigonometric polynomial of order 2, or generalized trigonometric polynomial. Sum of products of trigonometric functions, which can be rewritten in this form, and then we can, for real parameters, easily obtain zeros, also numerically or analytically. The location of the first three can be seen from this sketch. First, second, the third. And remarkably, on the interval, the initial non-local problem on the semi-axis is reduced to the third kind with this alpha. So we find, at least for real K1 prime or alpha, easily find eigenvalues, and also eigenfunctions in this form. And in the denominator, in this case, the series reduces to one term. And in the denominator, we have a term which can take zero values. And these zero values will be the above mentioned zeros and resonances. But this is clear. Interesting if we consider a formal problem with non-local conditions and with these non-homogeneous transmission conditions with U capital and V capital, then we immediately obtain its unique solution. And it will have singularities when the denominator vanishes, so at zeros of the denominator. But what is more, we can find the parameter set at which B is zero. And at this point, we will have invisibility. So outside the interval, the field will be zero, or the solution will be zero. So all the parameters satisfying this equation will provide invisibility of this interval. This problem has no direct physical meaning, but it is a very good to give a formal illustration of what is invisibility. So we can find both resonances and invisibility parameters using the analysis of the solution and its expansion coefficient. So now we proceed to acoustic and electromagnetic problems. Assume that we have a dielectric cylinder of radius A, or a perfectly conducting cylinder covered by a dielectric layer, the so-called Gubo line. A more general structure is this: many layers with different permittivities, and inside perfectly conducting a dielectric. It may be thousands of layers. Our colleague, Professor Alexeyev from Vladivostok, you may know this name, he wrote a book about these structures, recently published. So this is how it looks electromagnetically. So if we have a wire perfectly conducting, and if we cover this wire by anything, then this anything may be simulated by a layer of a dielectric with losses. And by solving this problem, we can explain the effects for a wire covered by a complicated grating or something, some complicated material. So this is a model problem with a layer on a perfectly conducting cylinder. So the problem statement is as follows. Also, we have a dielectric radius geometrically given in polar coordinates like this. And if we introduce this parameter, piecewise constant, and if we consider the polarized field so that it is enough to determine one component of the electric field, then for this component, we have this boundary value problem. Actually, it is one-dimensional on the semi-axis with non-local conditions. And in this case, we state the conditions in the form 16, and phi naught is given function, exponent, the so-called plane wave. And remarkably, this function can be decomposed into Bessel functions like this, using Bessel functions in the complex Fourier series. So this is a complex Fourier, and coefficients are Bessel functions. I believe the origin of the Bessel functions is this. Some 200 years ago, maybe, who was this? Who discovered this? But I believe Euler knew this. This is an extremely fast convergent series. The convergence is 1 divided by n factorial. And outside the circle, the solution has this form Hankel functions, 17. And this may be taken as condition of infinity, not Sommerfeld condition, but this condition, 17. So, Evgeny, this is a difference. We take this condition, not exponential decay, but this very condition is a condition at infinity. So, with this condition, we can assume that K naught is any complex number. But if K naught is real, then it is Sommerfeld condition. It's okay. So, we consider first azimutally independent solutions depending only on R. Then we have this already familiar to us, BVP on a semi-axis with these conditions. But instead of sign, we have Hankel. And one can consider this problem at any non-zero complex value of parameter K naught. And this problem has a physical meaning of finding oscillations and resonances. And let me just note that if we consider internal problem in a circle, internal, then eigenfunctions will be Bessel functions, and eigenvalues will be zeros of the Bessel function. And these zeros will play a role also for external points. So we look for solutions of the above mentioned problems in this form, Fourier series, and we obtain this in the external domain, this, and we have to find C and D and B and D. And if we have the simplest possible perfectly conducting cylinder, then the solution coefficients have this form. And we see that zeros of the Hankel functions are eigenfrequencies of a perfectly conducting cylinder. This was known many, many years ago. And the question is how to find zeros of Hankel functions. For n equals to 0, we have zeros, and Kerimov studied zeros of Hankel functions. But for higher order Hankel functions, I don't have reliable information about complex zeros. N equals 2, 3, I don't know. Maybe the first zero. So it's not easy. Anyway, the meaning is clear. If we proceed to dr, these are, by the way, the Hankel functions on the left. And we see that, just to mention, real parts of zeros of H0's Hankel function coincide with zeros of the Bessel function. And the imaginary part is constant. So they are situated on the line in the complex plane spaced by pi. But for n equals 1, I don't know at this moment. And this is how the resonance behavior looks like. When we have blue curve with stars, we are far from the resonance because we have real parameter. But when we are close to resonance, red circles, then coefficients as well as solution demonstrate clear resonance behavior. So we have resonances and sharp increase of the solution norm and sharp increase on the moduli of the coefficient. This is typical. And this is how the asymptotics of the far field asymptotics of the solution looks like. We observe resonances which everyone knows from the spectrometer picture. This is what we have. And this can be explained completely by associating resonances with zeros of Hankel function. So this is clear. And this is a typical picture. So for dielectric cylinder, the coefficients are like this, and the denominator is the so-called weighted generalized cylindrical polynomial, the sum of products of cylindrical functions with a weight. Zeta is it is proportional to the coefficient in the operator. And the question is to find zeros of this function, both real and complex. And the denominator is the weighted sum of products of cylindrical functions. But the difference is that we have Hankel here and Bessel. The question is zeros of the delta n. And we studied zeros of delta n. By the way, for the covered cylinder, I just keep it will be the same structure, but the function will be more difficult. But the idea is the same. And if we have many layers, it will be more or less the same. But we begin from the dielectric rod. And so I skip So for a dielectric cylinder, we proved the existence of complex zeros situated in a circle centered at zeros of the first Bessel function. So in a vicinity of every zero of the first Bessel function, there is one complex zero of delta naught, which is responsible for high quality resonance. And these are 20 complex zeros for 20 different values of the problem parameter. So they are here in the vicinity. And this is not the end of the story. One can immediately find complex zeros if to take into account that delta n vanishes when zeta takes these values and kappa. So we can find immediately numbered pairs when delta n vanishes, when here this vanishes and this vanishes, and then we can find more eigenvalues, more zeros by considering solutions to the Cauchy problems, applying parameter continuation. This approach works very well. So you don't need to prove any theory. So this theorem was not very easy, but more or less. But here you have obtained the result immediately. You have resonances without calculations. You have everything immediately. And then you apply parameter continuation and find resonances at wider parameter range. For invisibility, we can consider zeros of functions fn of zeta or fn of kappa. It is easy to check that these functions have many positive zeros alternating with zeros of the Bessel functions and some other properties. And we can, what is interesting, we can prove that the 5 first expansion coefficients vanish simultaneously when this condition holds. So J1 zeta kappa equals J1 kappa equals 0. It's a so-called critical reference points. So if we write this system, you immediately see that all 3 equations are satisfied at these parameter values, reference values. The last line is not seen, but it is okay, it's zeros of the Bessel. So this result demonstrates the possibility of finding the invisibility parameters without calculations immediately. And then to use this information to find more eigenvalues by parameter continuation. And this is how the parameter continuation looks like. And this is how the solutions look like. Very nice pictures. I skipped some. So a typical picture is like this. So each curve corresponds to implicit function 0 of a particular index n. And they merge at points marked by yellow squares. And yellow squares are points of invisibility. It's a very typical picture of the eigenvalue dependence on parameter. And they look like ladies have, how do we call it in English? When you have this cassette. Girls make long, you understand that. So this is this effect. This is exactly what we have. Mathematically, implicit functions generated by these Cauchy problems have the form of merging curves. And I understand that this is a kind of a background information. This is what we have for the simplest problem. They look very beautiful. And we have many such results. And at this point, I finished the first part of the lecture. So finding resonance and anti-resonance parameters by solving analytically or numerically certain equations involving cylindrical polynomials, sums of products of cylindrical or trigonometric functions. A big problem here is to solve Cauchy problem in the complex domain when we have to parameterize by a complex variable. When zeta is complex, this is not easy. You have to solve an initial value problem in the complex domain. And we are doing this now, but numerically, sometimes you need a supercomputer because you must use a very small step to obtain a reasonable curve in the complex plane. So my PhD or former PhD student, Hungarian, he uses 10 million steps to find the solution when zeta varies on a unit interval. Very, very small step because it's a very unstable process. And mathematically, implicit function of a complex parameter is a mapping, the map from the complex plane zeta to complex plane kappa. And this map is given as a solution to a differential equation with the initial condition. So we, at this point, come to the theory of singular mappings. So it may be very deep mathematically. And phi n is a ratio of two such generalized polynomials. Now I proceed briefly to the second part. When we have not a circular, but a cylinder of arbitrary cross-section, when we consider gamma a closed smooth curve or piecewise smooth, making exactly one term, something like this. And eigenvalue problem 45, 49 with this condition at infinity, not Zonderfeld, this type. So K and epsilon may be arbitrary complex numbers. For a circle, we solve this problem. But if we have not a circle, but an arbitrary closed contour, what to do? And we propose an approach here. So we know what is H1 and 1 Hankel functions, and we consider classical solution. And epsilon is a piecewise constant parameter. And we consider actually two problems, 45, 46, 47, 49, and the 45, 46, 48, 49, two different problems, TAP and TE and H, two different problems. We introduce Green's functions of external plus internal minus domains of this differential operator. And we assume that for the internal domain, it is clear, but for the external, we assume that the same holds. And this imposes limitations on the type of the external domain. There is a class of domains, external domains, for which 50 holds, but not for any domain. So this is a limitation of the method. So we can completely separate the singularity up to the boundary. For the internal problem, we know that we can, for a wide class of domains, separate both the geometric singularity and the singularity in parameter. So to represent Green's function and also trace on the boundary in the form 51, logarithmic plus the singularity associated with an eigenvalue of the internal problem. Eigenvalues of the internal problems form a discrete set of real numbers, positive numbers. So in the case of a circle, these will be zeros of Bessel functions. So proceeding from this representation, which is valid for a wide family of domains and contours, we define Green's potentials in this form. And then before to obtain an integral equation over the boundary, we introduce this operator over the boundary gamma with a logarithmic circle and the appropriate Hölder spaces, H beta gamma and H beta 1 gamma, Hölder spaces. And I refer to the book by Gävle and other mathematicians. They studied in detail this operator. And we can introduce a parameterization of the contour and represent this operator in the form of this logarithm sign operator and the rest with a continuous kernel. And we can, of course, represent this part as a purely logarithm plus the rest by multiplying and dividing with theta minus tau. This is also possible. And then we use Gävle's lemma. I believe this lemma was known before. So operate this operator with logarithm sign is continuously invertible, and the inverse is given by this Karleman type formula, and the norm is a constant. And particularly in these spaces, W1 to L2, the norm is 2. I believe this is a well-known fact. And then we will use these facts to consider boundary integral operators. So assuming that the contour is such that homogeneous equation with L has only the trivial solution, but there are contours, the so-called resonance contours, when your logarithm has non-zero solution. But we exclude this from the consideration. It may be included. And applying Green's potential, we reduce more or less immediately the BVP in question to the boundary integral equation 59 with this operator. And x0, y0 are on the boundary. And then we prove that this operator K lambda is a Fredholm finite meromorphic of F on a certain manifold associated with the first Riemann, the first principal sheet of the Riemann surface of the Hankel function or logarithm function. The sheet complex plane with a cut along the negative axis, like for logarithm theta. And we have an equivalence theorem. Each characteristic number of OVF K lambda is an eigenvalue of, we consider only H in this case. So we replace the analysis of eigenvalues with the analysis of characteristic numbers. And then we prove some auxiliary facts using the results published by Karchevsky and co-authors, that some sets on the complex plane of the spectral parameter are free from eigenvalues, and the spectrum, but this is a repetition of the Fredholm theorem, that the spectrum of eigenvalues is a set of isolated points. And then we proceed to essential part. So we represent K lambda in the form of the meromorphic pencil associated with an eigenvalue lambda s and completely continuous operator, logarithm plus degenerate kernel operator and this singularity. And then we study this part, this pencil. And then we prove the following. Pole pencil has one simple pole, it is clear, and one, what is not clear, characteristic number, which has this form, where US is the image of the inverse applied to eigenfunction trace NS, and this is an inner product over the boundary. So this is the formula for the pole pencil characteristic number. So if we have this eigenvalue, we can calculate pole pencil characteristic number. And we even present the proof. The formal proof is clear. If we consider this eigenvalue equation, then if we apply inverse, we have this. And if we exclude lambda, we obtain the third form. So the proof is very, very clear. And we confirm that K lambda is a finite meromorphic operator admitting separation of simple pole pencils. And then we prove the lemma concerning the location of the pole pencil characteristic number with respect to an eigenvalue of the internal problem. So roughly, eigenvalues are located on the real axis, and we can put every eigenvalue into a circle which contains only this eigenvalue. And then in this very circle, there will be maybe complex, but we prove that it is a real characteristic number of the pole pencil. By the way, we can separate another form of the pole pencil with beta operator S, which can be inverted also explicitly, and then we can obtain this formula for characteristic number. And this formula can be applied when we expand the eigenfunction traces in complex Fourier series. Then we can obtain exact formula for the image under the action of the inverse. And this quantity enters the formula for characteristic numbers, and then we can use it to calculate characteristic numbers in terms of Fourier series. And some formulas are here. So we can introduce in what follows the length of the contour, and we can use this length as a parameter. For unit circle, it will be 2 pi a, of course, this length. And then we can prove this theorem. So if we have a vicinity of an eigenvalue of the internal problem for the Helmholtz operator, and its radius can be estimated using the preceding lemma. And if we assume that the following condition is satisfied, then the total multiplicities of of characteristic numbers of k lambda and ps whole pencil ps lambda in this circle, in this disk, coincide. And this means that because each of them has a pole in this circle, that k lambda also has a characteristic number inside a circle of a certain radius containing eigenvalue of the internal problem lambda s. In other words, if the contour length is not very large, characteristic numbers of the pole pencils may be used as good approximations for characteristic numbers, that is, eigenvalues of the initial value problem. For disk, we have proved this in a different manner, but for disk, it's reasonable to consider how it looks like. The Green's function looks like this. So this is Green's function representation in polar coordinates. And it can be, logarithmic singularity can be separated. And then we use this formula, by the way. This formula is known, yes? Cosine logarithm, cosine Fourier series for logarithm. And then we can find, of course, poles coinciding with zeros of the Bessel functions. And then we can describe the above mentioned operators in this form. So this is a meromorphic part. We denote by T the pole pencils here. S is the operator associated with the circle. And then we can apply, for the external problem, by the way, Green's function looks like this in terms of Hankel functions. Then we can calculate the, I think better to skip the details, calculate characteristic numbers of pole pencils using Fourier expansions. And in the end, we can go back. Let me, here maybe. In the end, we can go back to the initial analysis in terms of the zeros of functions delta n, which I have mentioned. And they will coincide with the eigenvalues determined using pole pencils. This, it is mentioned here. So the zeros obtained in terms of pole pencils for a disk coincide with zeros of these functions, which I considered in the beginning. And this result was independently mentioned in this paper by Misawa and Korsers. Maybe I can remove this, but this is not extremely important. We can read the title. So they obtained a similar result independently. It was published in Science. So more specifically, for a disk, a subset of eigenvalues will be located in the vicinities, which we already mentioned in the beginning, of zeros of the first Bessel functions, denoted here by J1L, zeros of the first Bessel functions. And those zeros may be more or less efficiently calculated using the parameter continuation method. And these are complex zeros of this function on the complex plane kappa. parameterized by increasing real part of the parameter zeta. Zeta physically is a refraction index. So zeta varies on a certain interval. So permittivity varies from approximately 1 to 5. So we have a certain curve in the fourth quadrant of the complex Kappa plane. So zeros or resonances look like this. And these are zeros in the first column of the first Bessel, characteristic numbers of the Paul pencils, and difference between characteristic numbers and zero. So the proximity characteristic numbers of Paul pencils give good approximation for the sought eigenvalues, at least in the case of a disk. Actually, one may start with these quantities for a disk. And by the way, here we see that the distances will be actually pi between zeros of the Bessel functions. Easy to handle. And this is how it looks like. You can substitute parameters to the series. Series are rapidly convergent with exponential rate. So this is the effect of suppression. So when there is no suppression, we have a field in the shadow zone like this. And we have, and when 5 first harmonics are suppressed, we have much lower field behind the cylinder, but inside we have an increase. So physically, due to an interference between resonances of the internal and external domains, we see the effect of cloaking or invisibility, which looks like this. We have a conclusion here, but the conclusion is not very interesting. It is clear. I see here several problems that may be attacked. We may consider more complicated structures and in the complex domain. And the challenging problem, of course, is when gamma is arbitrary curve, or for example, a circle with a certain deformation, circle, something, and circle, or a flower or something like this, how to find eigenvalues and resonance frequencies. But this is a problem, how to find eigenvalues of the Laplacian in the arbitrary domain. This is a problem which was attacked by many scientists, and the problem remains. And one of conclusions is that if you want to know resonances of the external domain, you need information about resonances of the internal domain. And then you have good approximation using characteristic numbers of Paul pencils. So thank you. I'm in time.
Thank you very much for a nice talk, valuable talk. So now, we will discuss. You are welcome. Advance, discuss. If you have some questions, please. So, do you have question? Advance? No question. No. Okay.
Maybe I have a question to my colleagues. Do you know the works of mathematicians who considered dependence of the Fourier coefficients on parameters? Respective colleagues may know.
Well, what kind of parameters?
Any parameter of the, if we consider a boundary value problem, then the domain may be described by some parameters, or just as it is, consider a trigonometric series in which coefficients depend on one parameter.
So if so, what is interesting question? Suppose coefficients depends on parameters. So what we want to know?
For example, how the norm of the solution depends on this parameter. It may be sharp fall or sharp increase at certain parameter values. The solution norm, it's energy, roughly. But anyway, this is just one of questions.
I don't remember the number of slides. You were telling about that denominator, there was delta, and then you were interested to show that this delta is not equal to 0. So what was it?
So, for example, here, external expansion in terms of coefficients C and D. And in the simplest case, it is a ratio to functions. And zeros of the denominator are resonances. And a more complicated case, we have a more complicated function. But it's zeros, again, eigenvalues and resonances.
Did you show that this delta n is not 0, or so this delta n?
Yeah. First, we can separate two cases. When zeta is real, if zeta is real, delta n has no real zeros for any n. This can be proved. No real zeros for real zeta. The first result. The second result, if zeta is complex, then we have sufficient conditions when delta n has complex zeros, isolated. So outside isolated complex zeros, which exist only for complex zeta, delta n is not 0, and we have unique solution of the problem. When zeta is real, then it is always unique.
If delta n 0, what will happen? Do we still have solution?
No, the solution does not exist.
No, maybe there should be some extra condition like orthogonality. You know?
Yes, maybe. But so our approach is not as general as you mentioned. So we only specify the values of the parameters at which the solution is singular with respect to the coefficient in the equation. But if we consider the solution exactly at this value of the coefficient, then non-uniqueness will be. But if you apply additional, then maybe it will be unique. It's like in algebra. But in our approach, if delta n is 0, then the solution has a singular point with respect to the parameter in the coefficient. Like in the spectral method, exactly.
Okay, thank you.
So thank you very much. More question? No question. Thanks again for your nice talk.
Thank you.
We hope to meet you in next seminar. Okay.
Yes.
Thank you very much for participation, all my friends from different countries. Thanks. You can find time
from Tashkent, from Tashkent and from other cities.
No. Different countries.
Different countries. Yes, from different countries.
I see from Europe. So thank you very much.
Thank you. Goodbye. Goodbye.
Yura, do you know Kazanov? Yura, do you know Kazanov from Novosibirsk?
I know, yes.
Yeah, and his 70th year's birthday will be in Tashkent in October. If you can come to Tashkent, we'll be very happy. That is, I think, 10th October.
Thank you very much, Ravshan.
Invitation, I will send you invitation.
Thank you very much. Why not? I will be in Sweden. I will be in Sweden.
Yeah, I know. Okay, I'll send you the invitation.
Thank you, Ravshan. Thank you.
Thank you.
Bye. Bye.
So this is finishing. Yes.